Hello APC Mechanics students, Unit 2, Newton's Laws of Motion, Class 11, the elevator problem. Then Section 1, the elevator problem. A student is standing on a platform scale in an elevator. The aim of this section is to interpret the reading of the platform scale with respect to the state of motion of the system. The important thing is that, independent of the state of motion, the platform scale always read the magnitude of the normal push exerted by the scale on the student and not the pull of gravity Fg. This is a very important statement. Usually a misconception happens that we think that the platform scale measures the pull of gravity of the student, and this is not true. However, the platform scale measures the normal push, and this is important. We know that the normal push is a variable force, and it happens sometimes equal to the pull of gravity. However, if we have some perturbations to the system, like additional forces or acceleration, the normal push in this case would change. Then the reading of the scale will change with the state of motion because the normal push is a variable force. Remember that speeding up, it means that the acceleration and motion, which is velocity, have the same direction. Slowing down, acceleration and motion, which is velocity, basically have opposite directions. The net force F net have the same direction as A due to Newton's second law. F net is ma. Now, a student standing on a platform scale in an elevator, the forces acting on the student would be the pull of gravity and the normal push. And let me represent the FPD of the student in case 1 if there is no acceleration. So in this case, if there is no acceleration, then we're talking about two things: either the velocity is constant or zero velocity. And in this case, the pull of gravity would be equal to the normal push, and notice that I have represented them equally in the FPD. Now, case 2, if the acceleration is up, what would happen in this case? We also have the pull of gravity and the normal push, but if you look carefully at Newton's second law, F net is ma. So basically here, what do we have? If the acceleration is up, so we have the normal push to be up, the pull of gravity to be down. So we would say that Fn, if I'm talking the positive, up is the positive direction minus the pull of gravity, is ma, and this is positive, which means that because the acceleration is up, the normal push is up would be greater than the pull of gravity. So the normal push would be greater than the pull of gravity, and notice that in the FPD I have represented them such that Fn is greater than Fg. Now the third case, if the acceleration is down, so if the acceleration is down, we would expect that the force which is acting downward should be greater than the force acting upward, and in this case we say that the pull of gravity is greater than the normal push, and I have represented the normal push to be less in magnitude. Notice that for the three FPDs I have represented the pull of gravity to be equally. Why? Because neither the mass nor g changes, which means that Fg remains the same. However, the only thing that changes is the normal push. In the case of zero velocity, they would be perfectly equal. If it's accelerating up, which means forces up is greater than forces down, which means that Fn is greater than Fg. And if it's accelerating down, which means forces down is greater than forces up, which means Fg is greater than Fn. We're still in the elevator problem. Now let me continue. While the student is standing on a platform scale in the elevator, the following plot shows the variation of the reading scale with respect to time. Now here we have these two blips, A and B, and the scale reading. Basically this reading of the scale would be the normal push, and sometimes it would be equal to W or greater than W or less than W. So let's interpret that. If the blip is up, which means, notice that the scale reading is the normal push, then the normal push would be greater than W. So the meaning of these, first let me explain the meaning of these blips. Blips A and B, means that the elevator is accelerating either up or down. Now I will interpret them more. And in case where the curve is just horizontal, this means constant reading means Fn and Fg are balanced, and hence the scale is measuring Fg in this case. So let's talk about the blip A. Since the blip A is up, this means that the normal push compared to W, which is the pull of gravity, the weight, is greater than the pull of gravity, then the acceleration is up. And for a blip P, since the blip is down, this means the pull of gravity. So this is the pull of gravity. The normal push is greater than the pull of gravity. The normal push is less than the pull of gravity, which means the acceleration is down. Then now exercise 1. For the rest of the video I will be solving exercises related to the elevator problem and the drag force. A person of mass 70 kilograms is standing in an elevator that is moving downward. This is the person represented by dot. The motion is downward, so V is down. The speed decreases. The speed decreases means that V and A have opposite directions, then A is up. The speed decreases uniformly from 4 meters per second to 0 in 2 seconds. Then the initial speed is 4, the final speed is 0, and the duration is 2 seconds. What is the normal force acting on the person? So in order to determine the normal force, we need to utilize the FBD of this person. So let me represent the forces acting on the person. We have the pull of gravity is down. We have the normal push is up. Notice that I have represented the normal push to be greater than the pull of gravity because acceleration is up. Then now let me solve for Newton's second law. F net is ma. We have the pull of gravity. The normal push is ma. So A is up. Then that would be minus mg plus n equals to ma. And in this case, the normal push would be given by ma plus mg. In order to find the acceleration, we need to utilize the problem in kinematics. And they're telling that the speed decreases, changes uniformly, which means it's uniform varied motion. Acceleration can be determined given that we have the final and the initial speed plus ax multiplied by t. The final speed is 0. The initial speed is 4. The acceleration is unknown and the time is 2. So in this case, the acceleration will be given by minus 2 meters per second square. This is the acceleration as a vector quantity. Here we're utilizing a as a scalar. As the magnitude. Now let me factor the mass. That would be a plus g. The mass is given by 70. A is 2. G is 10. Now plugging that on the calculator, that would give you 840 in newtons. So remember that here, because I'm considering the positive direction to be up, then and A is up, then we need to replace A by the positive value given by 2. Now exercise 2, a student of mass m is standing on a scale plate placed on the floor of an elevator. When the elevator is not moving, the reading n of the scale is n is mg, and this is expected. Why? Because forces are balanced, n is mg. At some later time, the elevator is moving upward with the speed v. Then this is the student. It is moving upward, so v is up, slowing down, acceleration is down. We have the pull of gravity should be greater than the normal push. Okay, why it is slowing down? Okay, we have represented A to be downward because it's slowing down. Based on this data, which of the following statements about n must be correct? And this can be utilized using Newton's second law. F net is ma. We have the pull of gravity. The normal push equals ma. Now down is positive because the acceleration is down. That means mg minus n is ma. So isolating for n would be given by mg minus ma. Factoring out m, that would be g minus a, and the correct expression in this case is e. A person stands on a scale in an elevator. He notices that the scale reading is less than his usual weight. Which of the following could possibly describe the motion of the elevator? So n is less than the weight. Alright, so the acceleration is down. It is moving downward and slowing down. If it's moving downward, then velocity is down. Slowing down, which means acceleration is up, and this is wrong. It is moving upward and slowing down, so v is up, and because it's slowing, so acceleration is down, so partly b would be correct. It is moving upward at a constant speed. This is wrong because acceleration would be 0, and this would yield to a result which is w is equal to n. It is moving, so this is also wrong, and the correct answer would be b. A 4 kg box is accelerated upward by a string with a braking strength of 80 newtons. So the tension in the string, the maximum tension that the string can handle is 80 newtons. Acceleration is up. What is the maximum upward acceleration that can be applied on the box without breaking the string? Then basically we need to find the acceleration knowing that Tmax is 80 newtons, and this can be done by utilizing the FBD of this box. We have the tension to be up, we have the pull of gravity to be down, and I should represent the tension to be greater because it's accelerating up. F net is ma, so we have the tension, we have the pull of gravity, which is ma. Positive is up, then that would be T minus mg is ma, and we're searching for the expression of a. Then a would be given by T minus mg divided by m. The tension is 80. The mass is 4. All the answer seems to be perfect. Then let me take g to be 10 minus 4 multiplied by 10 divided by 4. That would be 40 over 4, which is basically 10 meter per second square. So the correct answer in this case is D. If a 50 kg man stands on a scale that measures force in an elevator traveling up with an acceleration of g over 4, what will the scale read? We know that the scale reads the normal push. Then let's utilize the normal push from the FBD of this man. We have the pull of gravity, which is down. And I will say that the normal push would be greater than Fg because it's accelerating up. And we would say that F net is ma. We have the pull of gravity, the normal push, equals ma. Up is positive, then that would be minus mg plus n is ma. And we're searching for the expression of n, which is the reading of the scale. N would be m factored out 8 plus g. Then the mass, which is, okay, before replacing the mass, that would be g over 4 plus g. Mass is 50. 10 divided by 4 plus 10, and plugging this expression on the calculator, we would get a value of 625 newtons, which makes D to be the correct answer. Exercise 6. A sphere of mass m is dropped from the top of a building and reaches the ground before achieving terminal velocity. The force of air resistance that acts on a sphere as it falls is given by F is minus kV, where k is a positive constant and v is the velocity of the sphere. What happens to the magnitude of the sphere velocity and acceleration, and to the distance it falls during each second as the sphere approaches the ground? The object is moving, so the object will cover a certain distance. So basically, distance will always increase. Alright, so we can directly eliminate this, and we're left with A, B, and D. In order to understand what's happening, let's recall the graphs that represent the variation of the velocity and acceleration with respect to time in such type of problems. If the positive direction is chosen to be down, we know that the velocity would increase, reaching an asymptotic value, and the acceleration would decrease until it reaches a zero value. This is the Vt, this is the At. Now, because velocity and acceleration in this case, they are both of them in the positive direction, so whenever we're talking about the variation of the velocity, it's exactly the same as the variation of the speed. Whenever we're talking about the variation of the acceleration, it's exactly the same as the variation of the magnitude of the acceleration, because both v and a are in the positive direction. We know that in this case the velocity increases, so we can directly eliminate this. Now notice that they're not talking about the velocity, they're talking about the magnitude of the velocity. Let me repeat and say again. If the velocity is positive, then the variation of the velocity is the same as the variation of the magnitude of the velocity, which is the speed. If the acceleration is in the positive direction, then the variation of the acceleration is the same as the variation of the magnitude of the acceleration. We differentiate between the variation of velocity and the variation of the speed whenever velocity is negative. The acceleration in this case, it decreases, which makes B to be the correct choice. Exercise 7. An object of mass 0.5 kg, which is the inertial mass, is given an initial velocity and then slides across a horizontal surface. The object experiences a resistive force that is function of velocity. The velocity v as function of time is given by that. Whenever we have velocity explicitly as function of time, that's good. Why? Because kinematics quantities, both position and acceleration, can be determined from velocity in terms of via calculus, and in addition to other quantities like force. For example, we have the value of alpha and beta to be constants. Which of the following is the correct expression of the net force in newtons? So basically, force is ma, and a can be derived from v using calculus, and that would be d by dt of alpha e minus beta t. That would be alpha d by dt of e minus beta t, and we know that the derivative of e to the power u, that would be u prime eu, because this is a functional. We need to multiply by the inner derivative, which is minus beta. That would be minus beta alpha e minus beta t. Now f in this case is given by minus m beta alpha e minus beta t. Let's replace the values. The mass is half, beta is 2, alpha is 3, alpha is 2, beta is 3, alpha is 2, and beta is 3. No need to use the calculator because this would cancel with this, and that would give us minus 3 e minus 3t, which makes B to be the correct answer. A student is investigating the motion of a coffee filter as it falls to the ground through the air. The student is using a motion detector to gather data for the motion of the coffee filter as it is dropped from rest. The mass of the coffee filter is m. The magnitude of the drag force of the air on the coffee filter follows the equation Fd is kv square, where k is a positive constant. Which of the following is the correct expression of the terminal velocity of the coffee filter? We know that at the terminal velocity or the exit velocity, forces are balanced. What are the forces acting on the filter? We have the pull of gravity down, we have the drag force which is up, and we can determine, remember that the terminal velocity can be determined by two ways. Either we consider the balanced forces at the terminal velocity, or if we have the velocity explicitly as function of time, we can take the limiting cases in which t tends to infinity. So in this case, we can say that Fd equals to Fg. They are balanced forces at the terminal velocity. Fd is kv square, Fg is mg, and we're searching for the value of v. Then v is given by mg divided by k, and the correct answer would be D. And finally, exercise 9 as an exit ticket for today's video, and luckily we're gonna solve a differential equation on this one. The object of mass m shown above is dropped from rest near Earth's surface and experiences a resistive force of magnitude kv, where v is the speed of the object and k is a constant. So it is dropped from rest. Then the initial speed in this case is 0. Which of the following expressions can be used to find v as function of time? Assume that the direction of the gravitational forces is positive. We know that in order to solve v, we need to utilize the differential equation of the system, and this can be done by starting with the Newton's second law. So let me take you through the different steps. We have the FBD, so we will say, okay, F naught is ma. We have the pull of gravity, the drag force is ma. I will consider the transient state in which the pull of gravity would be greater than kv and the positive direction is down. So I would say mg minus kv is ma. And notice that we're trying to search for v, but we have two unknowns, the v and a, and we don't have any additional equation to insert in our system. Then we need to convert this equation into a differential one. Then mg minus kv is m dv by dt, which means m dv by dt plus kv is mg. And let me normalize this differential equation by representing the first derivative in the canonical form, dividing by m, dividing by m, dividing by m. That would be dv by dt plus k over mv equals to g, because m cancels with m. I'm not telling you to memorize the way that we solve such differential equations, but remember different necessary steps that we need to reach in order to solve for the solution. So the first thing after you have applied, so step 1 is to do Newton's second law for the FBD. Second is to reach the canonical form. After that, we need to separate this equation by separation of variables, and probably this is the first time we're doing it. We have done it previously when this member was given by 0, not mg or g, and we have done that using the separation of variables. Now let's do this in the case where the second member is g. We will move this to the other side, and we would have that dv by dt is g minus k over m multiplied by v. The next step is to perform the common denominator for the right member. That would be mg divided by m minus k over m v. Now we will factor out 1 over m, which is mg minus kv. Now let's isolate the variables. This is mg minus kv, which depends on v. Let's take it down. And this is dt. Let's take it up. And it would be like that. And now we are ready to integrate on both sides. So this integral completely depends on v, and our initial speed is 0, so we will integrate from 0 to a final unknown speed v. And here we will integrate, so let me say that this is v, and here we're integrating from an origin of time which is 0, and because our variable of integration is t, we are integrating to a variable of time t, which means the correct solution is A. B is wrong because we have integrated from 0 to t along a variable v. We should integrate along the final speed v. Then that's it for me in this video, guys. See you soon in a new one.